So hi, I'm Abhineet and I work with eBay. Today I'll be presenting this paper designing distributed systems using Approximate Synchrony data center networks. This paper has been written by Dan Akepos, Jialin Lee, Vincent Liu, Naveen Kumar Sharma, Arvind Krishnamurthy. All these folks are from University of Washington. So goal of this paper is to implement more efficient replicated services by taking advantage of the features of the data center. So what this paper actually argues that Paxos uses dedicated leader to order the messages, and then fast Paxos rely on the messages to arrive in order. So this paper argues to use the structured, highly engineered network used in data center can themselves be used to order the operations in normal case. So to do that, first it defines that what is the total ordered multicast. So that if suppose there are certain process that multicast a message M followed by another multicast message M dash. So the receiving nodes should receive M dash uh, M dash. So the receiving node must process M before M dash because M was sent before M dash. So this is like a very strict constraint, right? Totally ordered multicast. So if we go from the totally ordered multicast to mostly ordered multicast. So what is mostly ordered multicast is if occasionally there are certain order violations. That is, uh, the receiving node receive M dash before M. So in that case, the paper says that in those small cases, either the client can take care of those scenarios, or the algorithm, instead of ordering the operations proactively, can actually, on detecting that there was ordering violation, it can then reconcile it. So first the paper describes, first part of the paper is basically mostly on the uh, infrastructure of the data center that can be used to order the operations. So it describes three design options for that. So first one is topology aware multicast. So topology aware multicast ensures all multicast messages to traverse the same number of links. So how it does is so suppose a node sends a message to aggregate node, and aggregate node is equidistant from all other nodes. So that is the way this topology aware multicast ensures that all the messages take same number of nodes to traverse and reach the receiver. Then second one is high priority multicast. So high priority multicast uses the topology aware multicast, but it also takes care of the cross traffic. So in this case, it uses high quality of service mechanism to prioritize the uh, messages. So MOM messages are like very small in numbers, so they can be prioritized over the other traffic. So thus it overcomes that problem of cross traffic. And the third one is in-network serialization. So in-network serialization uses the above QoS priority, high priority multicast, plus uh, it routes all the packet through a single route. So when it routes all the packet through, suppose all the messages are going to a group of nodes. So those messages should go through a single switch, And what that switch does is it not only serves as serialization point, but also ensures that message uh, traverse through the uh, to the group through same uh, route, same path. So that it has both the advantage of ordering as well as the equal number of hops. Okay. So now evaluation of the MOMs, which we discussed. So there are three evaluations. The first one is that multicast sending rates are varied from 0 to like 200K. And if you see here, the network serialization, the pink one is actually in network serialization, the one which had the switch. So that absolutely has zero reordering. Blue one is actually the conventional IP multicast. So that goes from 5% to 25% of reordering. And the red one is topology aware multicast. So that is the one which takes equidistance. So that goes from around 0, I think 4% to around 0.1%. The second evaluation also shows similar results. So in this, what they have done is they have fixed the MOM sending to 50,000 per second. Message sending is fixed to 50,000 per second, and they have simulated certain background traffic for a network to have network utilization, and they vary it from 5% to 30%. So here also, if you see, the trend is similar. The highest is for reordering is for the conventional multicast. The in network is zero reordering, and then MOM QoS is lower than the red one, which is the uh, topology aware multicast. And the third one is in this, they vary here the packets per second, that is messages per second, and they keep the background traffic to fixed at 10%. So, and they vary it from 20,000 to 100K. So here also it shows similar trend that the best performance is for the MOM plus in-network switch serialization, and the green one is here also lower, that is the QoS one, where the priority is maintained, is lower than the topology aware, just topology aware one. Okay. So now we come to Spec Paxos, Speculative Paxos. So Speculative Paxos takes advantage of the infrastructure of the data center, and so Speculative Paxos is divided into three sub protocols. First is speculative processing, second is synchronization, and third is reconciliation. So first one is kind of that client sends all the requests to, just some overview. The client sends the request to all the replicas, and those are executed. Synchronization basically to move those, the client don't know that after they send the response to, sorry, replicas don't know that after they send the uh, response to the client whether they are in those messages have been committed or not. Synchronization is basically to move from speculation state to commit state. And the third one is reconciliation. So this we were talking about earlier, that why not do on when it is detected that there is ordering violation, why not um, do ordering that time. So reconciliation does that. It's a heavy lifting on part of the leader. So I forgot to add actually one thing, that is what all states are there for the replica. So this protocol defines 4 states for the replica. One is the normal state. So normal state allows spec processing of the node. So in the speculative processing, a node must be in normal state. And for reconciliation, the replica should be in reconciliation state. And there are 2 other states, recovery and reconfiguration. So recovery and reconfigurations are like when the node when the nodes are dead, or they are lagging behind. So though in those that is the phase they are in, and then they can be brought up to speed using certain mechanisms. Okay, so first one is speculative processing. So in speculative processing, as we discussed, that the client first sends the request to all the replicas. So all these the replicas execute speculatively the request, and then send a response to the client. So if we see, so here client waits for this quorum, which they call it a super quorum, f plus f by 2 plus 1. These many responses from the replicas. And if it receives that, it matches. So I will show what actually replica sends. So replica sends the sequence number, execution result, and the hash summary. So what replica does is it takes the request, it makes an up call to application code. So application code is actually within the replica only. So it makes the application code and gets the result, and it sends the result and the hash summary. So each record in the log has a hash summary. So hash summary is actually the previous hash summary n-1 plus operation, the current operation, that is the hash summary. And hash summary is necessary here because suppose for a sequence, if we compare hash summary of 2 replicas, so if the hash summary is equal, so that means those 2 replica till sequence S have executed the operations in same order. So that is why hash summary is necessary. So what this client does is, once it receives these many responses, it compares the hash for all the messages, that if they are equal, and then it accepts the response. And if it doesn't, if it finds that it receives lesser than the super quorum messages, or all the hash do not match for the super quorum, then the client initiates a reconciliation process, the third one. Okay, so next phase is synchronization. So till now what happened is the client sent the request, the replica sent the response back to the client. Committed, but replicas don't know whether the messages, the response has been committed or not. So it is still in a speculative phase. So synchronization. So synchronization happens periodically. So one of the node which becomes the leader either does synchronization after some milliseconds or after k messages. It sends this message sync version of the log and the sequence number highest sequence number, and view is the view number actually. And then all these replica send back the response from okay, sends response with the view number, sequence number, and a hash which they have. And then here also actually super quorum is required, that is f plus f by 2 plus 1. So the leader waits for the super quorum, a number of responses, and then once it receives, it sends the commit message with view number, sequence number, and the hash to all the replicas. So as we saw in speculative phase that it matches the hashes for all the messages. Here also the leader matches the hashes for all the messages. And in case the leader did not find uh, the complete match or the super quorum, or if any node receives a message which whose hash does not match its own hash, then it initiates reconciliation. So reconciliation is a longer, I mean, more cumbersome phase as compared to synchronization and speculation. So reconciliation, in the reconciliation, suppose a replica starts reconciliation. So what it does, it sends the start reconciliation and the view number to other replicas, and then this replica sees the message, and this starts the uh, it starts sending to other replicas um, the message. And in this way, if a replica receives suppose f number of messages, uh, reconciliation messages, so it then sends the reconciliation this message reconcile v is the view number sent by, and the vl is the its current highest view number and then the entire log it sends to the leader. So the leader who owns the highest view number, the replica sends this message to the leader. So here if you see, so in this case the leader does not wait for the super quorum. So leader only waits for f replicas. So and what does leader do? So this slide describes that what does how it merges all the logs. So what does leader do is first one is committed entry. So if it sees so if the leader got f number of log entries, logs actually from f replicas. So first it will take the first it will take the log with the highest number of records, okay, and then it takes the committed entries. So all the committed entries are by default considered that they have to be in the combined log. So they are straight away taken. And then the second, it takes for sequence S, it takes the entries, and it matches the hash for those entries. If it is for the majority, then those hash are also put into the combined log with the phase as speculative. So commit entries were written with phase as commit, committed entries, and then the rest. Third one is that whatever other entries are remaining in the log, it takes all those entries and orders them in any order. in arbitrary order and then puts them in a combined log. Okay. And yeah, so this is how it forms the combined log, and then it sends the combined log to all the replicas. Evaluation. So this one is latency versus throughput. So throughput is varied, and if we see here, so in case of Spec Paxos, so it goes till around 90,000. It has low latency, whereas fast Paxos and Paxos have lower latency, um, till like I think 40,000 or a bit less than 40,000. So this is because in speculation phase, it's taking like two messages only, right? So that is why uh, it is lower for that till a long, the latency is lower till a long time. And Paxos plus batching eventually, like it is better than other versions of Paxos, um, from 40,000 to 100K, and then it achieve, like it also gives higher latency for throughput higher than 100K. And this is the second evaluation. So in this case, they vary the uh, packet ordering. So this is, they have simulated this packet ordering. So if we see that for Paxos, basically Paxos and other versions, it's almost constant. Throughput is almost constant. So fast Paxos does decrease a bit, uh, but there is some drop in fast Paxos. But Spec Paxos drastically decreases from uh, it was like 100K or so at this through reordering rate 0.001%, and it goes drastically down to 10,000. So this is because of the reconciliation. Reconciliation is a cumbersome phase. So, and more reconciliation means more uh, toll to the performance. Yeah. So yeah, thank you.